Alrighty then, let's have a look at AC power. When you look at the information that's provided, you'll see there are three tabs: DC power distribution, AC power distribution, and information about the sine wave. And all of these will play a part in answering these questions. In the sine wave, first of all, at any particular time, we look at the peak voltage times the sine of the angle. So I am going to bring up my calculator here because we're probably going to need that, and I'll bring that in and out as necessary. So moving down here, goes through some examples, talks about the relationship frequency is 1 over period, period is 1 over frequency, goes through a couple of examples of that which are also in the questions. When we come down here and talk about radian and grad, which I've actually never seen used, if we look at a sine wave in terms of a number of degrees, we see that one complete cycle, which is 2 alternations, is 360 degrees here. In terms of radians, it's 2 pi radians for a complete trip around the circle. And grads, it's 400 grads is one complete cycle, which is also called a period. When it comes to power distribution, it talks about a little bit of history, talks about the relative efficiency of higher voltages versus higher currents, and gives some examples of these things. So let's go ahead and get started, shall we? So we'll click on begin, and we see the first one. The peak voltage is 76 volts. The instantaneous voltage at 47 degrees is, let's get our calculator, bring that in here, and we will put in 76 volts. Actually, let's go ahead and clear that. Let's do it this way. Let's put in 47 degrees, take the sine of 47 degrees and multiply that times 76. When we do that, we get 55.58, which is option number 4. Correct. Question number 2, unit of measure for frequency. It's given in the information, is the hertz. That would be number 3. AC power can be distributed efficiently over long distances by using transformers. We use transformers to step up the voltage so that we can send it more efficiently, since higher voltage is easier to send than higher current. So we will go with number 2. Period of the sine wave in figure 1 is 5.263 milliseconds. The frequency then is going to be 1 over that. So let's get our calculator and we'll put in 0.005263, getting the milli out of it, and we'll take 1 over that, and that should give us the frequency. So the frequency, 190.005 hertz. Number 4 is 190 hertz, so we'll pick number 4. DC power can be efficiently distributed. Number 2, for only short distance. That's the advantage of AC. It talks about that in the history. Electrical power is most efficiently distributed with high voltage, much potential, but very little actual kinetic energy. So when we talk about voltage versus current, it's easier to send electricity with higher potential because not actually doing anything yet. So you can think of it that way. Okay, so on to the next. The frequency of the sine wave in figure 1 is 190 hertz. We want the period. The relationship there is reciprocal, so we'll bring up our calculator and put in 190 hertz and press the 1 over x button, and we get 5.263, strangely familiar from a previous question, 5.263 milliseconds, which is option number 1. Continue. Thomas Edison supported DC over AC. It's in the history because of the greater risk of electrocution with AC. In fact, Edison was, the legend has it that Edison spent some time in the streets of Philadelphia electrocuting animals to try to prove that DC was safer than AC. So option 4, correct. Frequency of the sine wave is 200 hertz. The period is going to be 1 over 200. 1/2 is 5, so the answer better have a 5 in it. Only one answer does, so I'm going to pick answer number 1 without doing any math. The frequency of the sine wave in figure 1, oh, we just did that one already. Okay. Peak voltage in figure 1 is 174 volts. The instantaneous voltage at 0.4189 radians is some value. So now we've got a couple things to do here. First thing we need to do is convert radians to degrees. So we're going to use proportionality, and we're going to say that if we have 0.4189 radians, and that's equal to some certain number of degrees, when 2 pi radians, or 6.28 we'll go with, 6.28 radians is one trip around, one complete 360 degrees. So really, this is 0.4189 divided by 6.28, which gives us the portion of the circle, and then we're going to multiply that times 360 degrees to get our actual number of degrees, and we come up with 24 degrees. So let's take the sine of 24 degrees and multiply it times 174 volts, and that will give us 70.8, and we have 70.772, so I'm going to select option 4. Now you remember, if that went a little bit fast for you, it's a video, so you can always stop it and replay it or slow it down. Next question. The time to complete one full AC cycle is known as the period. So that would be number 2. One full AC sine wave cycle is completed in 360 degrees, because remember, it's really just a side view of a spiral or a circle. Frequency can be defined as how many cycles we can complete in a period of time. In this case, it's the number of cycles completed in 1 second. So we will go ahead and put number 3. One full AC sine wave is completed in, we saw the picture when we first started the video, 400 grads. So we'll pick number 2. Now, I did mention when we went through that, I've been working on this stuff for 30-some years, and I have never, ever seen the term grad used in industry. So, in one ear and out the other. Let's move on to the next. The unit of measure for period. Period is a measure of time. Only one of these is time, so therefore it's going to be number 1, the second. Peak voltage in figure 1 is 116 volts, instantaneous at 341 degrees. Let's grab our calculator, and we will take the sine of 341 degrees, so put 341, take the sine, and multiply that times 116 volts. That gives us minus 37.765. Here we have minus 37.766. We'll take number 4. One full AC sine wave cycle, complete circle, 2 pi radians. Transformers are used to increase and decrease a voltage. So step AC voltage up or down. Transformers don't work with DC because transformers are really just inductors, and inductors look pretty much like short circuits for DC, so they're not going to do anything. Only AC provides reactance and allows that transforming function to occur. So we will pick number 2. Power is to be transmitted over a long distance transmission line. The most efficient voltage and current combination would be the highest voltage and the lowest current. So we're going to pick number 1. Remember, 5,000 volts is not what we use in our house, but a transformer can easily break that down from 5,000 volts at 20 amperes to 120 volts at a considerably larger amount of current. So we will pick number 1, highest voltage, lowest current. And the last one, finally we made it through. The period of the sine wave in figure 1 is 3.448 milliseconds. The frequency is the reciprocal of the period. So let's grab our calculator one more time and we will put 3.448 milliseconds. So let's see. 3.448 times 10 to the, oops, I think I messed something up there. Let me go ahead. I'm trying to put an exponent in, and I guess maybe this is it. 3.448 exponent minus 3 for milli equals, I'm not liking that either. So let's just do it the way I did it before. That's the thing about calculators. If you don't have one that's easy to work with, you're going to fight it all the time. So I'm going to put in 0.00348 and do that conversion myself. And I'm going to do 1 over x to get the frequency, 287.35. So we'll go with 290, number 3, 290 hertz. And it's correct. We can go ahead and skip the disk storage. We got 100 points. Awesome. So do not print. We're all done. Hopefully that will help you as you work your way through the AC power module. Later.